Welcome to the Edexcel Combined Science Chemistry Paper 1 revision video. In this unit, we're going to look at atomic structure and the periodic table, bonding, quantitative chemistry, chemical changes, and energy changes. Every atom has a tiny central nucleus containing protons and neutrons. Protons have a positive charge and a relative mass of 1. Neutrons are neutral, also with a mass of 1. Electrons orbit the nucleus in the shells, so they're outside the nucleus. They're negative and they have almost no mass. The atomic number tells you how many protons there are, and the mass number is protons plus neutrons. Because the positive protons and the negative electrons balance, an atom overall is neutral. Exam questions often ask what is inside the nucleus, and you must answer only protons and neutrons. Electrons are never in the nucleus, they're always in the shells outside. Developing the atomic model. The atomic model has changed as new evidence has come in over the years. Dalton started with solid spheres. Thomson in 1897 gave us the plum pudding model with electrons embedded in a positive ball. Rutherford's gold foil experiment showed something different, a tiny dense positive nucleus with mostly empty space around it. Bohr then placed electrons in fixed shells, and finally in 1932 Chadwick added the neutron. If the question gives you data from an experiment, link the data to the conclusion. For Rutherford, most alpha particles went straight through, so the atom is mostly empty. A tiny number bounced back, so there must be a small, dense, positive nucleus. Electron arrangement. Electrons fill shells from the inside out. The first shell takes 2, the second takes 8, and the third takes another 8, so 2, 8, 8. We call that electronic configuration. So argon with 18 electrons has the arrangement 2, 8, 8. The number of electrons in the outer shell equals the group number, from 1 to 7. A full outer shell is stable, which is exactly why the noble gases in group 0 are so unreactive. When asked to draw or write an electron configuration, always use commas between the shells, like 2, 8, 1 for sodium. Examiners deduct marks for writing 281 as one number. Isotopes. Isotopes are atoms of the same element with the same number of protons but different numbers of neutrons. So they have the same atomic number but different mass numbers. Two examples, carbon-12 and carbon-14 both have 6 protons, but carbon-12 has 6 neutrons and carbon-14 has 8 neutrons. Isotopes have identical chemical properties because their electron arrangement is the same. Periodic table. The periodic table is arranged in order of atomic number. The vertical columns are groups. Elements in the same group have the same number of outer electrons and react in similar ways. The horizontal rows are called periods, where each row has one more electron shell than the last. Metals sit on the left, non-metals on the right. Group 1 are the alkali metals, and Group 7 are the halogens. Group 0 are those stable, noble gases that don't like to react with anything because they've got a full shell. If a question asks, why do elements in Group 1 all react in a similar way? The answer is always the same. They all have one electron in their outer shell. Same number of outer shell electrons gives similar reactions. Mendeleev. Mendeleev arranged the elements in 1869 in order of atomic weight, but he did something clever. He left gaps where the pattern broke, predicting that undiscovered elements would fill them later. He was right. We now arrange the table by atomic number, not by atomic weight, because that gives a tidier pattern with no exceptions. 2 marking points come up again and again. He left gaps for undiscovered elements and he predicted their properties. The modern order is by atomic number. Mendeleev guessed, Moseley measured. Mendeleev predicted, later work confirmed atomic number was the right ruler. Group 1 alkali metals. Group 1 metals all have 1 electron in their outer shell, so they react in similar ways. As you go down the group, reactivity increases, and that's because the outer electron is further from the nucleus and shielded by more shells, so it's easier to pluck or to lose that electron. With water, they fizz, produce hydrogen, and form an alkaline solution. Lithium gently, sodium quickly, potassium with a lilac flame. When asked why reactivity increases down group 1, the marking points are outer electron further from nucleus, more shielding, easier to lose. Halogens. Group 7 halogens all have 7 outer electrons and exist as diatomic molecules, Cl2, Br2, and I2. At room temperature, chlorine is a green gas. Bromine is an orange liquid, and iodine is a grey solid. Reactivity decreases down the group. It's the opposite of group 1. And this is because the outer shell is further from the nucleus, so it's harder to gain an electron. A more reactive halogen displaces a less reactive one from its salt. Group 0, the noble gases, sit on the far right of the periodic table. Helium, neon, argon, krypton, and xenon. They all have a full outer shell of electrons, which makes them very stable and unreactive. They're colourless gases at room temperature and exist as single atoms, not molecules. Going down the group, the boiling point increases because the atoms get larger. In the exam, the classic, why are group 0 elements unreactive? That question always wants the same wording, and it will be because they have a full outer shell of electrons. Remember, group 0 or group 0, or the noble gases as they're also called, has nothing to gain and nothing to lose. States and particle arrangement. In a solid, particles vibrate in fixed positions. In a liquid, they're close together, but they can move past each other. In a gas, they're far apart and move freely in all different directions. As you heat a substance, you give the particles more energy, so they break free of those fixed or closed positions and are able to change state. State changes do not change the particles themselves, only their arrangement and movement. Mass is conserved when you melt or boil. Separating mixtures. A mixture is just 2 or more substances mixed together. They're not bonded or chemically joined, so they can be split apart by physical processes. An example of a physical process is filtration. You can separate an insoluble solid from a liquid. Insoluble means it does not dissolve. Something like sand in water. If you have a solid that does dissolve in a liquid, you gently evaporate the liquid, and this leads to crystallization. Simple distillation separates a solvent from a solution. So that's when you have 2 liquids, such as ethanol, in water. And what you do is boil the mixture, and then the liquid with the lower boiling point evaporates, leaving behind the liquid with the higher boiling point. You might be familiar with fractional distillation of crude oil. If you're asked which method to use, look at what's being separated. If it's a solid in a liquid and the solid does not dissolve, then you filter it. If the solid is dissolved in the liquid, then you crystallize it. If you've got a liquid in solution, then you distill it. Chromatography. Paper chromatography separates different coloured substances in a mixture, like dyes in a pen. Draw a pencil line near the bottom of the paper, put a spot of the ink on it, and dip the paper in solvent. The solvent rises and carries each dye a different distance. The RF value is the distance moved by the spot divided by the distance moved by the solvent. And an example of the solvent would be water or perhaps ethanol. Just a tip, always draw the start line in pencil. If you draw it in pen, the pen would dissolve and ruin the result. RF is spot over solvent. Both distances are measured from the start line. Ionic bonding. Ionic bonds form between a metal and a non-metal. The metal loses electrons to become a positive ion, and the non-metal gains those electrons to become a negative ion. The two oppositely charged ions then attract in a giant ionic lattice. Ionic compounds have high melting points, and they only conduct electricity when they're molten or dissolved in water. Molten is when you melt them, because that is when the ions are free to move. When asked why ionic compounds do not conduct as solids, the marking point is the ions are not free to move. Saying they have no electrons is wrong. Covalent bonding. Covalent bonds form between nonmetals by sharing pairs of electrons. Simple molecules like water and carbon dioxide have low melting points and do not conduct electricity. Giant covalent structures like diamond, graphite, and silicon dioxide have huge networks of atoms and very high melting points. Graphite is special. It conducts electricity because each carbon has a delocalized electron, so an electron that is free to react elsewhere. A question that is often asked is, compare diamond and graphite. The structure point is the same, 4 bonds in diamond, 3 bonds plus a delocalized electron in graphite. The property point follows next. Diamond is hard and does not conduct. Graphite is soft and does conduct. Carbon allotropes. Carbon forms several structures called allotropes. Diamond has each carbon bonded to 4 others, making it the hardest natural material. Graphite has each carbon bonded to 3 others in layers that slide, with 1 delocalized electron per atom, so it conducts. Graphene is a single layer of graphite, strong and conductive. Fullerenes are hollow carbon shapes, including Buckminster fullerene, which has 60 carbons in a ball. Nanotubes are cylinders of graphene. Spec names you must know are diamond, graphite, graphene, fullerenes, Buckminster fullerene, and nanotubes. Examiners can ask about any of them. It's the same carbon, different shape, different job. Metallic bonding. In a metal, positive ions sit in a regular lattice surrounded by a sea of delocalized electrons. Those electrons are free to move, which is why metals conduct both electricity and heat. The layers of ions can slide past each other, so metals are malleable. Alloys are mixtures of a metal with other elements. The different sized atoms disrupt the layers, which is why alloys are harder than pure metals. To explain why metals conduct, always use the phrase sea of delocalized electrons. free to move, and carry charge. That exact wording will secure the mark. Picture ions as floating balls in a sea of electrons. The sea conducts, the layers slide. This gives you both properties in one image. Conservation of mass. In any chemical reaction, no atoms are created or destroyed. They just rearrange. So the total mass of the reactants always equals the total mass of the products. A balanced symbol equation shows this clearly. The same number of each atom appears on both sides of the arrow. Always balance the equation before doing any calculation. If a mass appears to decrease during a reaction, the answer is usually that a gas has escaped. If the mass appears to increase, a gas has been taken in, and that's often oxygen. Relative formula mass. Relative atomic mass, or AR, is the number given in the periodic table. Relative formula mass, MR, is just the sum of all of the AR values in the formula. For water, H2O, that's 2 times 1 plus 16, which gives 18. That's the relative formula mass. For calcium hydroxide, you do 40 plus 2 lots of 16 plus 1, which gives 74. Remember to multiply the bracket. Brackets in the formula are one of the most common sources of error. If you see MgNO3 the small 2 outside the bracket multiplies everything inside it. Add them up, multiply the brackets. That single phrase covers about 90% of relative formula mass questions. Concentration. Concentration tells you how much solute is dissolved per unit volume of solution. The standard unit at GCSE is grams per cubic decimeter. The formula is concentration equals mass of solute in grams divided by volume of solution in cubic decimeters. Watch your units carefully. 1 cubic decimeter is 1,000 cubic centimeters. So if you're given a volume in cubic centimeters, divide by 1,000 first. The unit conversion is where most marks are lost. Always convert cubic centimeters to cubic decimeters first before you do the division. Yield and atom economy. Percentage yield is the actual mass of product that you make. It's divided by the theoretical mass times 100. Yield is almost always less than 100% because of losses, side reactions, and reversible reactions. Atom economy is different. It's the relative formula mass of the useful product divided by the total formula mass of all the products times 100. A high atom economy means less waste, which is what industry wants. Don't confuse the two. Yield is about how much you actually made. Atom economy is about the equation itself before you even start the reaction. Reactivity of metals. Metals react by losing electrons. That's oxidation. The reactivity series ranks from most reactive to least. Potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, hydrogen, copper, silver, gold. Silver and gold are very unreactive, which is why we like to use them for jewellery. A more reactive metal will displace a less reactive one from its compound. Metals less reactive than carbon, like iron, can be extracted by reduction with carbon. Metals more reactive than carbon, like aluminium, need electrolysis instead. When asked why aluminium is extracted by electrolysis and not by carbon, the marking point is aluminium is more reactive than carbon. Always link the method to the position in the reactivity series. Reactions of metals with water and acid. Reactive metals react with water to make a metal hydroxide and hydrogen. Only potassium, sodium, lithium, calcium and magnesium react noticeably with cold water because they're quite reactive. Less reactive metals like zinc and iron need acid. A metal plus acid gives a salt plus hydrogen, and you can test for hydrogen with the squeaky pop test. Copper, silver and gold do not react with dilute acid at all because they're so unreactive. When asked what gas is produced, the answer for metal plus water and metal plus acid is the same, hydrogen, and you test it with a lit splint and listen for the squeaky pop. Acids, alkalis and pH. Acids release hydrogen ions in water. Alkalis release hydroxide ions. The pH scale runs from 0 to 14. 0 to 6 is acidic, 7 is neutral, and 8 to 14 is alkaline. Universal indicator gives a colour for every pH. Red for strong acids, green for neutral, and purple for strong alkalis. When an acid and an alkali react, the hydrogen ion and the hydroxide ion combine to make water, and that is neutralization. An examiner tip: the ionic equation for neutralization is always the same. H plus OH minus gives H2O. Reactions of acids. There are 3 classic reactions of acids to know. Acid plus a metal makes a salt plus hydrogen. Acid plus a base, which can be a metal oxide or hydroxide, makes a salt plus water. And acid plus a carbonate makes a salt plus water plus carbon dioxide. The name of the salt comes from the acid. Hydrochloric acid makes chlorides, sulfuric acid makes sulfates, and nitric acid makes nitrates. Examiner tip: the carbonate reaction is the one that most students forget the extra product on. Acid plus carbonate makes a salt plus water plus carbon dioxide. 3 products, not 2. Metal makes hydrogen, base makes water, carbonate adds carbon dioxide. Each reactant brings its own extra product. Required practical: making a soluble salt. To make a soluble salt, you react an acid with an excess of an insoluble base. Warm the acid gently, add the base until no more dissolves, then filter to remove the excess. Heat the filtrate to evaporate some water, then leave it to crystallize. The crystals that form are your salt. Excess base means all the acid has reacted, so the salt is pure. In an exam, when asked why you use excess base, the marking point is to make sure all the acid has reacted. Filtering removes the leftover base, leaving the salt in solution. Electrolysis of molten compounds. Electrolysis splits an ionic compound, either molten or dissolved in water, and uses electricity. Positive ions move to the cathode, which is the negative electrode, and gain electrons. Sorry, cat lovers, but sometimes cats can be a bit negative, and that's how I remember that the negative electrode is called the cathode. Negative ions move to the anode. The anode is the positive electrode, and there they lose electrons, and that's oxidation. Oxidation is loss. Oil rig. Oxidation is loss, reduction is gain. Electrolysis is how aluminium is extracted from aluminium oxide. Examiner tip: the most common mistake is mixing up cathode and anode. The cathode is negative and positive ions are attracted to it. Opposite charges attract every time. Electrolysis of aqueous solutions. Aqueous means dissolved in water, so there are extra ions floating around. Hydrogen ions and hydroxide ions from the water itself. At the cathode, you get positive hydrogen, unless the metal ion is less reactive than hydrogen, in which case the metal forms. At the anode, you get the halogen if a halide is present, otherwise you get oxygen. Examiner tip: 2 rules to memorize. Cathode produces hydrogen unless the metal is below hydrogen in reactivity. The anode produces a halogen if one is there, otherwise you get oxygen. So less reactive than hydrogen, metal wins. If a halide is present, halogen wins. Required practical, electrolysis of copper sulfate. In this practical, you electrolyze copper sulfate solution using inert carbon electrodes. Copper ions move to the cathode and form a coating of copper metal there. At the anode, you get oxygen because sulfate stays in solution. Weigh the electrodes before and after to measure the mass change. If the electrodes are copper instead of carbon, the result changes. The anode disappears and copper transfers across, and that's how copper is purified industrially. Carbon stays, copper moves, oxygen escapes. 3 things happen, 1 at each spot in the cell. Exothermic and endothermic. Exothermic reactions release energy to the surroundings, so the temperature rises. Combustion, neutralization, and hand warmers are all exothermic. Endothermic reactions take energy in from the surroundings, so the temperature falls. Thermal decomposition and sports injury packs are endothermic. The clue is in the temperature change. In an exam, if the question says the temperature of the surroundings rose, then the reaction is exothermic. If the temperature fell, it is endothermic, and the temperature change is the giveaway. Reaction profiles. A reaction profile is a graph of energy against the progress of a reaction. For an exothermic reaction, the products are lower than the reactants on the energy axis, and that's because energy has been released. For an endothermic reaction, the products are higher, because energy has been absorbed. Both graphs have a hump in the middle, and that hump is the activation energy. Always label 3 things on a profile: reactants, products, and the activation energy. Lots of students forget the activation energy label and lose an easy mark. Activation energy. Activation energy is the minimum energy needed for a collision between particles to actually result in a reaction. A higher activation energy means a slower reaction. A catalyst speeds the reaction up, not by changing the temperature, but by giving the particles a different pathway with a lower activation energy. The catalyst itself is not used up in the reaction. In an exam, never say a catalyst lowers the temperature or speeds the particles up. The correct phrase is provides an alternative pathway with a lower activation energy. Required practical, temperature change. For the required practical, you measure temperature change for a reaction, like hydrochloric acid plus sodium hydroxide. You use a polystyrene cup because it insulates well, and a lid to reduce heat loss. Record the starting temperature, mix the reactants, then record the maximum or minimum temperature. Plot temperature against the volume of one reactant added, and the peak shows the equivalence point. In an exam, the 2 marking points for why a polystyrene cup are it's a poor conductor, so it reduces heat loss to the surroundings. Saying just it's plastic is not enough. Making water potable. Potable means safe to drink. In the UK, tap water starts as fresh water from rivers, lakes, or reservoirs. The process has 3 steps. 1. Filter the water through beds of sand and gravel to remove solids. 2. Sterilize the water using chlorine, ozone, or UV light to kill microbes. 3. In some places, add fluoride to protect teeth. If fresh water is scarce, seawater can be made potable through desalination. Distillation boils the water and condenses the steam, and this leaves the salt behind. Reverse osmosis pushes salt water through a partially permeable membrane. Both desalination methods use lots of energy, which is why they're mostly used only where fresh water is genuinely limited. In an exam, the marking points for fresh water are filter, sterilize, sometimes fluoridate. For seawater, it's distillation or reverse osmosis. Reversible reactions and equilibrium. Some reactions can go both ways. The reactants form products, and then those products can break back down into reactants. We show this with a double arrow. If a reversible reaction happens in a closed system where nothing can escape, the forward and backward reactions eventually reach the same rate. That's called dynamic equilibrium. The amounts of reactants and products stop changing, but both reactions are still happening underneath. In an exam, if asked what dynamic equilibrium means, the marking points are forward and backward reactions at the same rate, in a closed system, with no overall change in amounts. The Haber process. The Haber process makes ammonia from nitrogen and hydrogen. Nitrogen comes from the air and hydrogen from natural gas. The reaction is reversible. Nitrogen plus hydrogen makes ammonia with a double arrow showing it can also go backwards. The conditions are around 450 degrees Celsius, 200 atmospheres, and an ion catalyst. These conditions are a compromise. High pressure pushes the equilibrium towards ammonia, but that's expensive. Lower temperature also favours ammonia, but slows the reaction. The chosen conditions balance yield against cost. Ammonia made by the Haber process is used mostly to make fertilizers which help crops grow. Life cycle assessment. A life cycle assessment, or LCA, looks at the total environmental impact of a product from start to finish. It covers 4 stages. 1. Getting and processing the raw materials. 2. Making the product. 3. Using the product. 4. Disposing of the product. For each stage, you consider the use of natural resources, the energy needed, the waste produced, and the pollution caused. LCAs help us compare different products fairly. For example, comparing paper bags to plastic bags isn't as simple as it sounds. Each has different costs at each stage. Recycling reduces waste and saves energy compared to making new products from scratch. But recycling itself uses energy and produces some emissions. That's why a full LCA is needed to judge the real impact. And that's it, your Edexcel Combined Science Chemistry Paper 1. I hope you found the video useful and good luck in your exams.